So this is the WebGPU version of the lines demo, which as you can see is aliasing quite badly. Uh, I'm not sure why it is, because on the definitely to do with the monitor. If we make it bigger, not quite as bad, but there's definitely some issues there. I will look into that once I know, but let's have a look at the overall structure of the code. So what we've got here is the back end of this is that we're inheriting from the WebGPU widget that I've explained in a previous demo. Then we go through, so the first thing we do is initialize WebGPU. So if we go to here, so as with the previous points demo, we have to do a lot more low-level initialization and setup ourselves. So first thing we're going to do, get the default device. What the get default device does is it grabs the WebGPU device and sets everything up for us, ready to be used. Then we're going to initialize our buffers. So in this case, I'm calling the create lines. What that does is it returns this points array. Now create lines, this does exactly the same as the previous one does. It creates line pairs, but this time we're using the built-in NumPy functions to do it because it's quicker, more efficient. So we're grabbing the half width, half depth extents as we've done previously there. Then we're using linspace to generate evenly spaced Z coordinates for our horizontal lines. Then we're doing a pre-calculation of an array that's big enough to store all those data. And then what we use is one of the span functions, so basically using slices to copy the start and the end x's across the rest of the array there. And then we do the same for the z coordinates and pass those through. So in this case, they're just going to be the same each time. Then use the new axis is to create the z component in there. And then it's the same, we mirror the data for the vertical lines. Finally, we concatenate them together into a single array and reshape it into a flat NumPy array. Then notice here now it's the number of points we're interested in, because the draw functions, as we'll see in a bit, rely on those number of points. I then convert that vertex data into a NumPy array. I mean, really, I could have done that in here because we want to deal with everything in NumPy arrays, but I'm just converting it there into a 0.32. In fact, it is a NumPy array again, so that's most probably wasted. I'll investigate that. I might change that bit later. The key thing is we're generating a vertex buffer for WebGPU. So WebGPU has got two options. We can create a buffer and we can create a buffer with data. So in this case, it's the equivalent to the OpenGL calls. This is doing a malloc and a memcopy straight away, copying that data to the buffer. Unlike with OpenGL, we can do multiples at the same time in threads, whereas OpenGL can only have one active buffer because we have to bind it first. This is bindless, which is useful. So once we've got that set up, we go through to the next stage, which is to create the render pipeline. So the render pipeline describes basically how our data is laid out. It also describes the shaders and all the other elements. So first thing I do is I open the line shader. We'll look at the shader code in a little bit and see how it responds to this. And I create a shader module with that code. So the shader here, you can see it's got one binding group of uniforms, which is my MVP as a previous. My vertex in at position 0 is a vec3 of float 32s. So again, a bit like OpenGL, we've got input positions. My output from my vertex shader, in this case, is a position, which is a built-in thing. So this is the equivalent of GL position. In this case, we can name it what we like because this basically says is the thing that we're outputting. Then I've got vertex main, which is my vertex shader. All that's doing is multiplying the uniform MVP by my input position converted to a vec4. And then, as you can see here, my output shader is just setting the colour to white, as my previous one did. So again, it's fairly similar to the OpenGL. Once you get a feel for the languages, converting across isn't too difficult. So we now have to create our pipeline to explain how the data's set up, how it's laid out. This is in the form of basically a dictionary of information here. So we've got the create render pipeline, naming our pipelines. So when error messages go wrong, this will tell us which one. In this case, we're telling it to determine the layout from the shaders itself if it can. And then we say our vertex shader, we can find the code in this shader module that we've created. The entry point is vertex main, so that corresponds basically to main here, vertex main. So we can call that what we like. We're not limited like we are with OpenGL with having a main and that's the one that gets called. And we're also not limited to have them, different files. Then our buffers for this. So we're telling it the stride of the data, how to get to the next one. So we have 3 floats, 4 bytes per float. So our stride is 12. Our step mode is vertex. So that's just explaining how to get to the next vertex. And the attributes in this case are float 32s by 3. And it's at shader location 0. So basically that's giving us our sort of overall layout for our input data. It's a vec3. Vec3s have 3 floating point components, so that gives us the 12. Fragment shader module here is telling us again which shader to look for. Fragment main is the name of the shader, and in this case it's the target. What are we rendering to? And in this case it's just a texture, which is an RGBA 8 unsigned norm. Primitive type, so this is a list of lines. Again, it needs to know the type of data. And then we're adding here a depth buffer, so depth stencil buffer, and we're also enabling our multi-sample here with the MSA count. I think I need to do a little bit more work on this bit. I have got some other demos where I think I need to come this in, so might come back to this in a while with another lecture. This is my uniform buffer. So to copy data to the shader with uniform information in, unlike in OpenGL where you make individual calls to set uniform, we must always have a buffer that we copy across that data. Now there are lots of packing rules with this data which we'll encounter as we go into more depth on different things. For now we've got a single array of 16 floating point values, which is our matrix from our model view project, so it's quite easy. But later on, these sizes and how things concatenate together become very, very important. So we're going to create this again, another buffer with data. We tell it that this time, rather than it being a buffer for our uniform data, sorry, our vertex data there, this time we're telling it that it is a uniform buffer. So the data is uniform there. And all we're ever going to do is copy it to the destination. So we're giving it hints to say how we're going to use it. And then finally, the bind group basically tells the shader how these uniforms are bound when we're using them. Now, in this case, again, it's very simple. We've got one bind group, group 0. This is the first binding, and this is a variable called uniforms. So this is basically going to attach this uniform buffer to that position. Later on, we might have many buffers that need to be bound with different settings and different things in, and it gets far more complex, and we have to manage it. For these simple demos, it's quite easy. So that's set up our overall pipeline. We can now reuse this to do our rendering. So Paint Web GPU is called every frame to do our rendering. So the command encoder creates the command encoder. We begin our render pass, and here we're specifying our color attachments. So this is saying what we want to render to. In this case, it's our multi-sample texture view. And then our resolve target is our color buffer view. These are generated within the Web GPU widget itself. So these buffers are generated in here, and they are basically two buffers. One is used to render to, and the other is used to resolve it to. So one is going to be generated larger, and then there's filtering that happens to get it down to the smaller one, which should reduce our aliasing. As we've noticed, we've still got aliasing here, so I need to figure out what I've got wrong with that a little bit there. We've also now got our load operations. So when we load this render pass, clear, and that clears to this background color. And then when something's written to it, we store that value. We've also got a depth stencil attachment there as well. Then we'll update our uniform buffers. What that's going to do is it's going to recalculate anything with our uniforms. So recalculate the model view project matrix. So that's doing the calculations that we did on the previous one. And then we're going to rewrite this to the buffer. So the buffer is already staged. We created it previously. This is just going to update some new data. Typically, we might have hundreds of these buffers, and we'll only update small little bits of it each frame, and then the whole buffers will then get synchronized with GPU size. But in this case, that's the only small bit that we're doing. We're doing it every frame. Then we're activating the pipeline. Setting the viewport, so that sets a viewport to the size of the screen. We're setting the pipeline to activate the currently active pipeline we need. Enabling the bind groups, which is going to bind now the uniform data to copy it across. Activating our vertex buffer, so this is the vertex buffer that we want to do. And then we're just drawing. And in this case, we're saying draw however many elements that we've got there. End the draw, submit to the queue, and then update the color buffer, which will copy from WebGPU to us. Now, if I run this, oops, wrong one. I want to WebGPU lines, run this one. So again, we can see that there. If we go in and start changing some of this, so for example, we can do the same thing. We can say draw 0 to 10, like that. Oops, I got that wrong. Actually, 0 and 10. Hopefully that will do it. No, it's not wanting to draw. In theory, I should be able to draw the buffers there. It's not working. Let's just tell it to. Oh, let's just tell it to draw 10. Like that. And see what happens. Ah, there we go. So you can see I've drawn the 10 lines there. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So you can see it's doing the same thing there as before. There are other modes to the draw that allow us to pass in extra parameters to it, but I think it's a different command and I've forgotten what the command is off the top of my head. So we'll look at that at a later one as well. And put it back to the full draw there, and it's drawing. So this gets a bit more complex. Obviously, we have the widget in the back end doing quite a lot of work just to get everything moving and running correctly. And then we've got our pipeline that we have to specify ourselves and everything else. So whilst it's a lot more code to write, it does give us far more flexibility than the other versions.